Welcome. This is in continuation with takeoff distance. See, so far we are assuming that it's a single engine aircraft, but you will very well appreciate nowadays with bigger aircraft, high performance, we have got multi-engine aircraft. So we will be discussing something about twin engine aircraft. Suppose a twin engine aircraft is taking off, in the preparation for taking off, in the process of taking off, suddenly one engine fails. What should he do? How to handle this situation? But naturally, if one engine fails on the ground, you should apply the brake and stop the aircraft. But then you have to ensure that once the brakes are applied, that speed may be very high. So you need a very large runway length to really brake that aircraft to a full stop. So as a designer, you also have a responsibility to see what is that airstrip length minimum required to ensure that aircraft while taking off, even if it fails, if I apply a brake, it should be able to stop. If I could find out some speed as a reference speed, if the aircraft, one engine fails before that speed, then I should have sufficient length to brake and put to 0. If the aircraft engine is failing, one engine is failing, after a reference speed, then it should have enough excess power to climb and go for a circuit flying. If I do this and very cleverly optimize this, I can get a balanced field length, that is, which is safe for twin engine operation. I'll explain you this through a diagram. But before I do that, please understand one thing. If I have a twin engine airplane, so this is also giving thrust, this is also giving thrust, this is the center line. If suppose this engine fails, so what will happen? This thrust is operative, so it will have a yawing moment. The airplane will just turn like this. To ensure that it doesn't happen, I should be able to generate a moment in the opposite direction. Who will give that moment? Obviously, now we have got rudder, right? You know that? The rudder. There are two engines, one here and one here. Let's say right engine has failed. So what will happen? Because this thrust is operative, it will turn the airplane like this on the ground, which will be very dangerous. To ensure that it doesn't happen, I have to generate a moment in the opposite direction like this. Because of thrust, it will turn like this. To counter it, I need to generate a moment in this direction. So from top, because of this thrust, it is a clockwise moment it is coming. So I have to generate an anti-clockwise moment when I look from the top. So who would do this? It's only the rudder. Only the rudder could do this. Let's say, assume that this is the rudder. Assume the wing is in front. I am going like this. What type of moment I want? I want looking from the top anti-clockwise. That means force should be towards you. So I will deflect the rudder like this. If I deflect the rudder like this and plane is moving like this, the force will be acting towards you. That is, force will be acting like this. That will give a yawing moment anti-clockwise, and that will balance the disturbed or imbalanced torque or moment. So what is important? That your rudder of the airplane should be powerful enough to generate enough restoring moment to nullify the moment imbalance because of one engine failure. Okay? So that is first criteria. Second thing, we were looking for some critical speed, which generally, if you see some old literature, it is called VFR, or failure recognition speed. Okay? What is the meaning of that? Let us say the airplane has started from here. Okay? At some point it has failed. One engine has failed. Now for 1 second I will give him time to recognize that speed. He has to check. I told you if he is given a speed as a guideline, that dear friend, you check whatever speed at which one engine has failed. Please check that if it is less than VFR, then simply apply brake. If it is more than VFR, then go for climb or takeoff. When he goes for takeoff, you have to also ensure that the design should be such that even after one engine has failed, the aircraft should have enough excess power to climb up to a particular altitude easily, at ease. And these are as per the regulation. There are numbers for that, right? Because he should climb and then take a circuit flying, and he may land same airport or land in nearby airport depending upon the emergencies. Okay. So how do I select that VFR? What is that speed reference with which pilot will compare the speed at which one engine has failed, and he will compare and see if that speed at which engine has failed is less than VFR, then he will apply brake, or more than VFR he will go for takeoff, meaning thereby if the failure speed is less than VFR, he should have enough field length for making the aircraft to a standstill. If it is not, if it is more than that, then he should go for a takeoff. This is the understanding. But how do I get this VFR? That very important speed reference, which is a guideline for the pilot to ensure whether he goes for a takeoff with a single engine or applies brake and stop. If we do a theoretical exercise, let's say this is distance and this is speeds. If I try to plot trend of braking distance versus different initial speed. For example, suppose the airplane has just failed as far as one engine is concerned too early, and let's say the braking distance is this much. As the speed at which the airplane engine has failed increases, the braking distance will go on increasing. So let us say that variation is something like this. Okay, I can calculate, assuming different speed at which the engine has failed, and calculate the distance, braking distance, by using our formula SB. Okay. Now we are coming back to takeoff distance. Let us say if airplane is taking off, which has started from here, then it will take a longer distance for takeoff, little higher speed, little less distance. As the speed increases, so this will follow a trend something like this. Okay, this is distance for takeoff, and this is braking. We call it accelerated braking. This is clear, no? If I want to apply brake and stop the vehicle when the speed is very low, the distance will be low. As I started applying the brake at higher speed, the distance required to make it to zero will be more. Like that, this graph will be changing, and reverse in takeoff, it will be like this. For a smaller speed, I need larger takeoff distance. If I start at a higher speed, I will take a smaller takeoff distance because already I got a high speed. Right? But this is the point where both these distances are same, you see, and this distance is called critical field length. And this corresponding speed is called VFR. Let's try to understand this graph. This is VFR, failure recognition speed, at which your braking distance and distance to takeoff are same. That's why this is called critical field length or balanced field length. What is the interpretation? Suppose aircraft has failed at speed V1, the pilot will check. If V1 is less than VFR, then he will go for braking. If V1 is more than VFR, he will go for takeoff. As simple as that. And this way you can avoid many accidents. That is why for twin engine or multi-engine, the critical field length or balanced field length is so important. You know, by the concept of rudder power, that is, if one engine fails, it will give some yawing moment, and rudder should be enough powerful at that speed to ensure that the airplane doesn't do like this or like that while take off. At the same time, the designer must give enough bandwidth that even if one engine has failed, if the speed of the airplane is less than a particular speed, which is called VFR, then the pilot will apply a brake and go for braking. And if that failure speed is more than VFR, then he should take off. Okay? So the designer must ensure that the airplane has enough rate of climb even with single engine. Right? These things we have discussed. There's another important aspect for flying is, which is very important for designers to have a perception, is how an airplane to be landed during crosswind. Crosswind means suppose I am coming like this and the wind is coming from right to left or left to right. So natural thing will be the moment there is a wind from right to left, the airplane will be drifted like this. But you want to land at a particular airstrip, a particular mark. So how a designer should give that bandwidth where the pilot can easily manage? It should be manageable. If a designer gives the bandwidth that it can be managed, then pilot can manage. If that is not in the design, then pilot can't manage. So a designer should understand what are the ways to land in a crosswind. So let us see what is the aim. Aim is, suppose this is the airstrip. I am taking the top view. And pilot is to land here somewhere, central line, let us say. Suppose pilot is trying to land like this and there is a crosswind, whether this side, from this side or from that side. So there will be tendency of the airplane to be drifted this way or that way. But pilot has to land here. So what is the way to handle it? That is the question. Now I'll take you back to your class 9th, 10th, around that. Remember, if this is a screen and this is the center line and you are here, standing here, you want to shoot a bullet. And you are asked to hit this point. What will happen? If you aim your bullet exactly at this point, you know that it will never hit because of gravity, this will fall like this. So gravity is constantly pulling it down. So what is the clever way of doing it? Although you want to hit it, if you know how much gravity will pull it at this point, so aim some point higher. So if you aim there, then the projectile will go like this and bullet will go like this and hit. Right? This is one way to handle. I will try to utilize this for this case also. I have to land somewhere here. So I was going like this. Now because of wind, I will be drifted like this. So what I will do, I will select a separate line. Maybe I want to actually land here, so I will create an imaginary line here. I will make my all approach aiming at this line. Okay? So what will happen? Because I know because of the wind right coming from the right side, I will be naturally drifted towards left. So finally, what will happen? I will be flying something like this. I will be actually flying like this. I will try to go into the wind and ensure that through the thrust, this whatever force I am getting here get neutralized. But since I am just aiming at some other point here, which is not this point, because of this wind, I will be constantly drifted towards this direction. So at some point when I come here, I have to turn the airplane nose left, flare up and land. This is one way. So what is that way? If I want to land here, if I know wind is coming from right hand side, so I will be aiming at some other point here, other line here, knowing very well I will be drifted anyway back to this, like the example I have given it here. Similarly, if wind is coming from this side, so I will create an imaginary line here. My approach, I will try to approach this as the central line where I am going to land. Because of this wind, I will automatically get drifted. I will come near the central line. So the pilot with his visual aid, if they are not flying through an instrumental landing system, they will be applying corrections. Right? This is one way. Second way is I am flying like this and the wind is coming from my right. So I'll be drifted like this. What I do, I bank my airplane. And once I bank it, the lift vector is like this. One component of lift will try to resist this drift. And I go like this, and near the airstrip, I roll back, flare up, and touch down. Okay? In this landing, there is a problem. If there are some error, it may happen that the aircraft accidentally gets landed on a single wheel first. For lighter aircraft, of course, it's not a serious problem. But for a bigger aircraft, it may create a very serious problem. So pilot has to be very, very perfect in doing this. And third one is, we say, through side slip. That is, if this is the line where I'm going to land, I'll be let me draw it. I'll be actually flying with a side slip condition. We call it side slip condition. That is, I'm flying like this. My velocity vector is along the approach, and I'm flying like this. Okay, what will happen? If I fly like this, you could see that it will, relative air will hit this surface, and it will generate a force in this direction, and the wind was also trying to push it this direction. That way, it will nullify. Right? Again, as it comes near the runway, it has to turn like this. The moment it turns, there is a induced roll also. So you have to apply both aileron and rudder. Please understand, whenever you apply a aileron, suppose if I apply a aileron like this, I'm putting it down and putting it up, it will try to go like this. But what will happen as it goes like this, there will be a induced drag more here, so it will try to turn also. So always when you apply rudder or aileron, we call it cross stick. That is both the stick to be applied together. Okay? Thank you.